Physics, the energy of matter. So matter can store energy in a variety of different ways. Sometimes energy is stored in the form of chemical energy. Other times, like in the example of a spring, it's stored in mechanical energy or potential energy. If you have a wheel spinning or even a whole star spinning around, that's a massive amount of kinetic energy that's being stored in that way. But all of these amounts of energy are actually very small when you consider the amount of energy that is stored in the matter itself in the form of mass. So a famous scientist named Albert Einstein discovered a relationship between mass and energy. This relationship is given by E equals mc squared. You hear that one rattled off a lot. And basically it is energy equals mass times the speed of light squared. So this relationship is super important, but it is not quite as important as when you change it just a slight bit. And when you say E is equal to the change in mass times the speed of light squared. So E equals delta mc squared. This right here, the E equals delta mc squared, is the basic driving principle behind fission and fusion reactions. For fusion, basically what you have is two hydrogen atoms being fused together to create a helium atom. The mass of the two hydrogen atoms happens to be just a tiny bit larger than the mass of the new helium atom. This tiny amount of mass during this reaction is converted into energy. So basically heat and light and mostly just that. And basically this small amount of energy in the case of like fission power plants can be used to power our electrical grid. So to understand exactly how much energy is stored in mass, let's go ahead and do a small calculation. So suppose that half a kilogram of mass, half a kilogram is just slightly larger than 1 pound. Suppose half a kilogram of mass were to be converted into energy using fusion reactions. How much energy would this be? So, and just so you know, 1 pound is about 0.45 kilograms, so we're about a 20th of a pound, or about a tenth of a pound from being a tenth of a pound away from being 1 pound exactly. So for our knowns, we have mass is equal to 0.5 kilograms. Speed of light, it's a constant, doesn't change. And that is 3 times 10 to the 8th meters per second. And what we're looking for is we're looking for the amount of energy that this would produce if all of this mass were to be released as energy. And our equation here is of course E equals mc squared. So we can go ahead and plug in our numbers into this equation. We can say E is equal to 0.5 kilograms times 3 times 10 to the 8th meters per second quantity squared. When you do this, E comes out to be a very big number. It is 4.5 times 10 to the 16th joules. And this is a rather hard number to visualize, but basically the first atomic blast in World War II was about 10 to the 14th joules. For this, looking just at the exponent of the 16 and the 14, the energy produced by this is 2 orders of magnitude larger than the first atomic blast in World War II. All total, if you do the division, this means that half a kilogram of matter contains about 450 times the amount of energy used in the blast from that atomic weapon. So very, very large amounts of energy stored in relatively small masses.